Morning, myself K.Karthik. I am from second triple A section. Today's my topic is about diagonalization problem, repeated roots. Introduction to diagonalization. Diagonalization is the process of transforming a square matrix into a diagonal form. This technique simplifies many mathematical operations, including exponentiation, exponentiation, and finding eigenvalues. Understanding diagonalization is crucial for solving systems of linear equations and analyzing linear transformations. Importance of eigenvalues and eigenvectors. Eigenvalues and eigenvectors are fundamental in determining the diagonalizability of a matrix. An eigenvalue is a scalar that measures how a transformation scales a corresponding eigenvector. The relationship between eigenvalues and eigenvector is essential for understanding matrix behavior. Conditions for diagonalizability. A matrix is diagonalizable if it has enough linear independent eigenvectors. Specifically, an n into n matrix requires n linearly independent eigenvectors to be diagonalized. The geometric multiplicity of each eigenvalue must equal its algebraic multiplicity for diagonalizability. A matrix is diagonalizable if it has enough linear independent eigenvectors. Specifically, an n cross n matrix requires n linearly independent eigenvectors to be diagonalizable. The geometric multiplicity of each eigenvalue must equal its algebraic multiplicity for diagonalizability. Understanding repeated roots. Repeated roots occur when eigenvalue has a multiplicity greater than 1. This situation can complicate the diagonalization process scientifically. Proper treatment of repeated roots is essential for ensuring matrix diagonalization. Algebraic vs geometric multiplicity. Algebraic multiplicity is the number of times an eigenvalues appears as a root of the characteristic polynomial. Geometric multiplicity is the dimension of the eigenspace associated with a eigenvalue. A matrix is diagonalizable if the geometric multiplicity equals the algebraic multiplicity for each eigenvalue. Example of matrix with repeated roots. Consider the matrix A is equals to 2, 1, 0, 2, which has a repeated eigenvalue of lambda is equals to 2. The characteristics polynomial is lambda minus 2 whole square, indicating an algebraic multiplicity of 2. However, the eigenspace for lambda is equals to 2 has only one linearly independent eigenvector, leading to compensation. Eigenspace and basic formation. The eigenspace of an eigenvalue is the set of all eigenvectors associated with that eigenvalue. For repeated roots, the dimension of the eigenspace must be carefully assessed. A complete basics for the vector space is necessary for successful diagonalization. Constructing generalization eigenvectors. Generalized eigenvectors are introduced when there are not enough linearly independent eigenvectors They help from a complete basis when dealing with matrices with repeated eigenvalues. Generalized eigenvectors satisfy the equation a minus lambda whole power n v is equals to 0 for some integer n. Jordan form as an alternative. When a matrix can't be diagonalized, it can be transformed into Jordan form. Jordan form repeats the matrix in a nearly diagonal structure accommodating repeated roots. Understanding Jordan form is crucial for dealing with matrices that exhibit repeated eigenvalues. Steps to diagonalization with repeated roots. Calculate the eigenvalues and their multiplicities using the characteristic polynomial. Determine the eigenspaces and access the number of linear independent eigenvectors. If necessary, compute generalized eigenvectors to complete the basis for diagonalization. Practical applications of diagonalization. Diagonalization plays a virtual role in solving differential equations and systems of linear equations. It is widely used in various fields such as physics, engineering, and computer science. Understanding how to handle repeated roots ensure effective applications of diagonalization techniques.